Very nice. Hi everyone. Good afternoon. Thank you for choosing to attend this talk. My name is Xiangyu Bai, currently a second year PhD candidate from Department of Electrical and Computer Engineering at Northeastern University. Today, I'm going to present my research that titled Towards Generative Autonomous Simulation. Okay, without further ado, let's get started. Too long, don't read. Um, in a short sentence, autonomy simulators are bad. They're not fully developed and not easy to use. Generatives are models are good because they generate realistic photos, but are bad when you're considering that they don't really have temporal consistency when you apply them to the autonomous domain. Um, and very little research has been done for the video diffusion side. So what we did is we solved these issues by proposing a model that overcomes existing autonomous simulator limitations, enhancing the video quality, variety, and ease of use while ensuring high temporal and spatial consistency. Um, Now, let's talk about the background. The general realization from the academia in terms of autonomous domain is that testing the performance of autonomous vehicles in the real world is both time and cost prohibitive. And the data collection in edge and extreme cases are even more challenging than ordinary research group can afford. The overall consensus of the industry is that using synthetic simulators and datasets can somehow address this issue and helps aid in building a more robust and trustworthy autonomous navigation systems. However, our prior research indicates that using synthetic simulators and datasets presents another very significant challenges. The domain gap between virtual and real-world domain harms the reliability and robustness of the said autonomous navigation platforms and algorithms. We developed a platform called Scoping Autonomous Vehicle Simulation Platform, or SAVES for short, and its extension, SAVES Plus, to properly quantify and close the said domain gap. And in order to achieve our thorough analysis purpose, we co-developed world's first stable stereo generation method from the popular gaming engine GTA 5. We call it temporal frame swap, or TFS for short, and built a large-scale driving dataset to aid the purpose of thorough autonomous simulation analysis. As we mentioned, this research indicates that simulator-generated driving data, despite its high quality and diverse sensory modalities, the domain gap exhibits significant unreliability, thus limiting their effectiveness in aiding the development of a robust navigation platform. During our research, we found out that most of the autonomy simulators are closed source and require you to pay a hefty fee, and those who are open source and open to academia use typically is worse in terms of quality, requires significant resources and expertise, thus restricting its accessibility and applicability, especially in the research field. The recent surge of generative AI, and in particular video diffusion models, provides a scalable solution by helping us to create realistic driving videos with only natural language. However, our further analysis indicate that their temporal and spatial consistency is very bad, and there are not a lot of existing state-of-the-art research that covers this topic. And ensuring such temporal consistency is crucial for a lot of autonomous tasks, such as simultaneously localization and mapping, point tracking, segmentation, and object detection. Furthermore, the lack of accurate ground truths means that there is a significant challenge in terms of evaluating how well these generative models performs when it comes to adopting them as a synthetic autonomous simulator. A little bit of background in terms of image and video diffusion models. So diffusion models, if you haven't heard already, are a series of probabilistic models that are used to generate data that are similar to the training data. The diffusion itself adds Gaussian noise to data and then learns to reverse this process to recover the original data. At the very center of the diffusion process is the loss function, which compares a randomly generated Gaussian noise to the Gaussian noise obtained through gradually adding more and more noise to the original data. Through this process, the model itself learns how to reconstruct what you are required. We already know that with proper training and a large copious amount of data, diffusion models are able to produce detailed and accurate data while avoiding all of the complexities of the previous generation, which is adversarial training with generative adversarial networks, or GANs for short. And it has been a very popular research topic, especially in the recent years. In fact, if you're traveling to CVPR next month, you will see, I believe, half of the paper on the diffusion side. We would like to point out that during our research that diffusion models are mainly designed for images. And that leads to very bad temporal consistency when we try to adopt diffusion models to video domain. And furthermore, the dataset, again, although copious, are generic datasets such as ImageNet and etc., which are not autonomous specific, which translates to less than ideal results when we would like to concentrate the diffusion models to a very certain domain. Furthermore, well, if you dig deeper, there are also very few existing external conditioning video models featuring autonomous simulation, further making it difficult for us to use video diffusion models as a reliable way to generate synthetic data for autonomous navigation tasks. And good example here would be the videos shown below, which is some of the open source models that we can run. And when you try to ask it to generate a proper first person wheel in the driving scenario, it is relatively bad. So what did we do? We addressed these issues by proposing dual-conditioned temporal diffusion modeling, or DCTDM for short, which is a novel approach to generate realistic, high-quality frames and coherent, long driving scenes in video format with the respect to both temporal dynamics and the 3D geometrics of the scene, which you can see here is our pipeline and a video generated from our model. And how did we build this model? We did construct it using existing diffusion backbones, but we make significant and novel contributions and components to existing backbone. But first, we would like to make significant upgrades to existing 2D image-based convolutional and transformer-based architectures. We introduced a new temporal dimension and appended after the existing 2D modules to maximize the knowledge preserved in existing pre-trained weights. Furthermore, we introduced a spatial temporal transformer block that adaptively applies cross-frame attention to enhance video processing. It changes the way of applying cross-attention based on the dimension of latent representations, conserving computation resources if the dimension is very high. And we replace existing convolutional 2D spatial layers in UNet architectures with this new adaptive temporal spatial block, thus extending convolutional 2D spatial layers and capturing the motion and context of the driving scene across the frames. Next, we connect the temporal diffusion backbone with two additional conditioned temporal diffusion models with constraints, new frames to follow the underlying physical structures and appearances of the past frames. You can see on this model architecture that we select dense depth map and Kenny edge data as two ground truth conditioning, and the selection is by no mistake um, not arbitrary. Depth map provides the needed information to reconstruct the scene, and edge data provides missing details in the frame. And a more easy to understand concept example would be considering a stop sign on the road. While the depth map is able to capture the distance and the overall shape of the stop sign, it does not explicitly tell the model what characters are written on the sign. That is because as the words are printed on the sign, it with the surface of the sign has the same distance to the camera capturing the depth map. Therefore, nothing can be deducted from the map itself. Cutting edge, however, while it does not include the spatial and temporal information of the scene, it provides details, especially characters and symbols of the scene, and that compensates really well with the aforementioned depth map. And this is for that reason that we selected these two specific ground truth conditionings. And we expanded to be specific ControlNet with our 3D components that aforementioned UNet with expanded spatial temporal adaptive blocks, and gradually fuels the latent process through the ControlNet 3D to the stable diffusion backbone via the zero convolution operation. And with these external conditionings, we are able to generate videos based on ground truth data which makes evaluation so much easier. For the last part, we designed a novel joint reconstruction loss by computing the mean square error between noise extracted from the external conditioning components and the conditioned Gaussian noise generated from the backbone. And specifically, we use inverse depth scaling to ensure that closer objects receives stronger noise scaling. And the fact that we use the inverse depth map, again, provides feature points from closer objects, and Kenny Edge enables more consistent symbols throughout the videos and enables a lot of the details that are otherwise missing from the depth maps. To thoroughly train our model, we curated a very large scale and diverse driving dataset called Driving Scene DDM. And our training dataset integrates open source, real world, and synthetic data alongside some of our in-house collections. It comprises 121K videos spanning 29 diverse environments with diverse weather and time conditions. And we also provided textual scene descriptions, dense depth maps, and Kenny edge data for comprehensive autonomous system training. One of the good samples of the diversity of our dataset can be seen here, which is driving in the city at night with snow piled up on the side of the road, which is not a dataset that can be not some data that can be usually found in existing datasets. In terms of our result and evaluation, we adopted video distance and image distance to measure how similar in terms of quality and consistency of generated videos compared to, let's say, a ground truth video that are selected from our validation set. For example, here we compared our model with some of the state-of-the-art open source video diffusion models of similar scale, and you can tell that other than Cog Video X, our model pretty much excels in terms of video quality and consistency, indicating our model's superior performance. We also evaluated our model on odometry and clip similarity, aiding a lot of critical navigation tasks. With that, we conclude that DCTDM excels in terms of controllability, efficiency, and customizability, which we believe paves the way for generative autonomy simulations while aiding the generation of edge and extreme cases. Finally, we conducted an ablation study on the external conditioning of our DCTDM, thus evaluating the effectiveness of the added information. You can tell that using both depth and KNH data achieves the best performance, yielding highest stability and quality, and produces a video that pretty much aligns with our expectation when we mention data created from an autonomous simulators. And adding DCTDM in general greatly improves the temporal stability and overall video quality, which is indicated by, again, the FVD and FID values. And that is my presentation. We believe DCTDM aids in autonomous simulation tool to cover edge and extreme cases, and the expansion of data collection capabilities is an exciting avenue for the advancement of future autonomous models. Thank you.